Ladies and gentlemen, good afternoon. I'm Gabriele and I'm presentation. What have I to press? Oh, okay. And I'm going to talk to tell you something about testing permeability. I'm sorry because that we are late, maybe you are hungry, and this is not the best time to give you a technical presentation. I will try to do this light and hopefully not too boring. Please don't be too hungry with me at the end. Thank you. So I will give you a quick company overview, and then I will explain you about two different new patented techniques to speed up the measuring of permeability on packages and films. My firm, Extrasolution, is a spin-out company of the University of Pisa and is specialized in gas permeability tester. Our slogan is that we can test every object that has a barrier, and barriers is so important for food packaging because the barrier that the packages can do to the gas strongly affect the shelf life of the product. And not only this, imagine if you can calibrate the thickness of your film to give you exactly the barrier that you need, you can save material, you can save money, and you can reduce the waste. Our main subject is the innovation, and in fact we present on the market some innovative product like this one. You can test 3 different gases in only one unit. So oxygen, carbon dioxide, water vapor, that are the main gas of interest for company that works in food packaging. The advertisement has finished. So when we talk about testing permeability, usually the company has to face 2 main problems. The first one is that the measurements are going to take you a lot of time. And the second one is that you want to test a sample with very high barrier, so hard work for us. Look to the time. These are typical time that a measure on some material is going to take. For example, a standard PET 23 micron, 1 hour. Obviously, you cannot test this online. All these kind of tests are offline. You have to wait. Imagine the advantage that you can have if you speed up the test, because you know that in some hour you are producing kilometers of films and you cannot have the result and the production is running. It's very important. What about a film with aluminum? 5 hours. 4 days for 250 micron. Okay, nobody uses, fortunately. And synthetic cork for wine, 4 centimeter, 10, 20 days. I'm not joking, this is at the time. So, 2 patents. One is about the oxygen transmission rate on 3-dimensional object, packages. The norms claims that you have to run the test like this. You have to put you take your packages, you put the tubes inside, you glue it by epoxy resin, and you start to flow nitrogen inside to remove the oxygen that is present inside the package. What's happened? Imagine that is the thickness of your film. This is the side that is exposed to the air, and this is the side inside the inner side where you are flowing the nitrogen. On the beginning, the oxygen concentration is 21%, the concentration that you have in air, on both the sides. Then you start to flow nitrogen, and from this side, the oxygen concentration starts to decrease and go to 0. Then the molecules of oxygen get outside of your film, and you establish a gradient into the layer of your film, into the thickness. What you see is something like this. The oxygen concentration decreases and goes to the established value. Now you are the gradient established. Then you close these two valves and you flow the nitrogen directly to the sensor, and in this way you record the zero of your sample. And you see something like this. And the differential is the gas transmission rate. This is the standard. ASTM DIN standard claim this. This is our patent. So we started to think about what's happened if we don't use atmospheric to run the test, but we use a different value of oxygen concentration. In particular, what if we use an oxygen concentration that is 42 instead of 21? That is the one that is present in the atmosphere. What's happened? Look now. This is the film. The film is in the packages, is in the atmosphere. So I have 21% of oxygen along all the thickness of my film. Then from the inner side, I start to flow nitrogen. This side, I will have the same thing than before. The oxygen concentration will start to decrease and goes to zero. But what's happened outside, where now I have 42% of oxygen? In this case, the oxygen concentration starts to increase. So before I had something like this. Imagine this is a 21%. Now I'm having something like this. What's about the point that is exactly in the middle? This point doesn't change its concentration. So it means that it's like to have two different films with a thickness that is the same than before but divided by 2 that reach the equilibrium at the same time. And as the time of the permeation depends with the square of the thickness of your material, I have divided my thickness for 2, and I have reduced 4 times the duration of the measurement, simply changing the external concentration of oxygen. This is what's happened, the kinetic. This is with the standard method. This is with the patented method. So the equilibrium has reached in a time that is 4 times lower. But please have a look. Also the signal has increased, because the signal that you measure is proportional to the oxygen concentration that we are using. So in this way, you have solved 2 problems that usually the company has to face, because you increase the minimum level that you can test, the double, and you reduce 4 times the duration of the measurement. Is it possible to demonstrate with some maths that 42 is the best concentration to obtain this result? And this method works not only for monolithic materials, but also for multi-layer films. So we have only to adjust the concentration, because for multi-layer material, maybe 42 is not the best. But in any case, you will have a big reduction in time. So the main advantages: the measuring time is reduced, you have an increase of the signal, and you don't need to make a pretreatment of the sample, because you don't have to have the cleaning cycle anymore for your sample, because the cleaning cycle has become the measuring cycle. This is another one, and this is for testing the gas transmission rate to flat material. Okay? And this is for gases, not only for oxygen, different kind of gases. The norms claim that the measurement has to be done in this way. You have two chambers, and you put your sample in the middle. Then you start to flow nitrogen on both the sides to clean the sample, to remove the oxygen and the carbon dioxide that is present into the sample. You will see also in this case something like this. And then you start to flow the gas that you want to test, oxygen or carbon dioxide or something different, in the upper chamber, and the gas permeates through your sample. What's happened? The same than before. When you increase the concentration outside, immediately the external layer will increase the concentration on the surface, and then the oxygen will start to move along the thickness of your film, and on the end you will have a gradient. And you will see a graph like this. This is the gas transmission rate. These are the standard technique, a very new technique. How can we work this time? As I told you, true problem, increase the signal and cut the time. To increase the signal, the easiest way is increasing the concentration of the gas that you want to test. But for films, the norms claims that you have to work at 100% of concentration. How can I get 200% of concentration? We can work on pressure, because the signal depends also on the pressure. But I cannot increase the pressure only from one side, because we are talking about plastic material, so you will deform the material. But imagine that you increase the pressure from these sides, the pressure of the gas that you want to test. And on the other side, you increase at the same value the pressure of the carrier gas. This means that the differential in total pressure between the two sides of the film will be 0. But the partial pressure, so the differential that each gas has toward the other, will be maximum, because you have only oxygen, for example, from this side, and only nitrogen on the other side. So it's a good way to increase the concentration. What's happened? This is the standard technique, and this is what's happened if you use an arrangement like the one that I showed you before. The signal increase a number of times that is proportional to the number of pressure that, the number of times that I increase the pressure over the atmospheric pressure. But I don't cut the time. I have to think something more. If you have a look to the graph, you see that the signal increase and then start to decrease before to reach the equilibrium. Imagine it's like as when you go into a shower, okay? And you open the tap and you want 37 degrees. You can set the temperature and you can wait. But if you want to get quicker the water at the right temperature, you open completely the tap with the hot water, and then when the temperature starts to increase, you close and you open a bit the cold water. Exactly the same principle. If we increase the pressure a lot, and then when the establishment of the gradient has started, you decrease again the pressure, you will have the same effect than you have when you take a shower. The time to reach the equilibrium will be shorter. Same value, but shorter time. Okay, but before it was nice because I have a higher value. Now I have a short time, but the value is the same. So I don't have the amplification of the signal that I had before. Last step. I can increase the pressure and then I decrease, but a level that in any case is over the ambient pressure. In this case, I will catch both the advantages. I will cut the time and I will increase the signal. So the main advantages are we can short the measurement time. We can amplify the amplitude of the signal that we want to measure. And we can also set a very quickly test, for example, for quality control by setting a threshold. Thanks for your attention. I will try my best to not bore you too much.